Tonight, we're going to explore one of the strangest contradictions in all of physics. Light is the fastest thing in the universe. It escapes from almost everything. The only thing that can trap light is a black hole. But here's what almost nobody realizes. If you took enough light, an almost unimaginable amount of it, and focused it into a small enough space, that light itself would create a black hole. Not matter. Not a collapsing star. Pure light. Energy with no rest mass at all would warp the fabric of space-time so severely that it would trap itself forever. The very thing that nothing can outrun would become its own prison. And understanding how that's even theoretically possible changes everything you think you know about gravity, mass, and the nature of light itself. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. Light is fast. It's the fastest thing in the entire universe. Nothing outruns it. Not rockets, not particles and accelerators, not anything that has ever existed or ever will exist. Light travels at roughly 300,000 kilometers per second. In the time it takes you to snap your fingers, a beam of light could circle the entire Earth more than 7 times. It reaches us from the moon in about 1.3 seconds. It reaches us from the sun in about 8 minutes and 20 seconds. Light is so fast that for most of human history, people assumed it traveled instantaneously. You open your eyes and you see. There seemed to be no delay at all. And light escapes from everything. It flies away from stars, away from planets, away from the most violent explosions the cosmos has ever produced. Supernovae, the cataclysmic deaths of massive stars, release more energy in a single second than our sun will produce in its entire 10 billion year lifetime. And even from those explosions, light escapes effortlessly. It simply leaves. Nothing holds it back. There is exactly one thing in all of known physics that can prevent light from getting away, and that is a black hole. A region of space where the fabric of space-time itself is curved so severely, where gravity is so crushingly intense that not even light, moving at 300,000 kilometers per second, can climb out. A black hole is the only cage from which light cannot escape. So here is the question that should bother you. If a black hole is the only thing that can trap light, could light itself somehow create one? Could the very thing that escapes from almost everything build the one structure it can never break free from? It sounds impossible. It sounds like a contradiction, like asking whether water could somehow become so wet that it turns dry. But the answer, at least according to the mathematics of general relativity, is yes. Theoretically, yes. And understanding why forces us to rethink two ideas that seem simple but are anything but. We need to rethink what light truly is, and we need to completely rethink what gravity truly is. Because those two ideas are connected in a way that almost nobody expects. And that connection is the key to everything that follows. Let's talk about light. Not just the warm glow you see when you flip a switch, although that is part of the story. Let's talk about what light is at its most fundamental level, down at the scale of individual particles and fields. Light is electromagnetic radiation. It's a ripple, a vibration, in something called the electromagnetic field, a field that exists everywhere in the universe, filling all of space. When that field oscillates, when it vibrates at a particular frequency, we perceive the result as light. Different frequencies give us different kinds of light. Low frequencies produce red light, the kind of warm glow you see at sunset. Higher frequencies produce blue and violet light. Go below red and you get infrared radiation, which you feel as heat. Go lower still and you reach microwaves, and then radio waves. Go above violet and you enter the realm of ultraviolet radiation, then X-rays, and finally gamma rays, the most energetic form of light in the universe. All of these are the same fundamental thing. They're all electromagnetic radiation. They all travel at the same speed. And they're all made of the same basic building blocks. Those building blocks are called photons. A photon is the smallest possible unit of light. It's a particle, but not in the everyday sense. Photons don't behave like tiny marbles bouncing around. They also behave like waves, spreading out and interfering with each other. This wave-particle duality confused physicists for decades in the early 20th century, and it remains one of the strangest features of quantum mechanics. But for our story tonight, the important thing about photons is this. Each photon is a discrete packet of energy. It carries a specific, well-defined amount of energy that depends on its frequency. Higher frequency means more energy per photon. A photon of blue light carries roughly 1.5 times the energy of a photon of red light. A single gamma ray photon can carry millions of times more energy than a photon of visible light. This relationship between frequency and energy was first described by the German physicist Max Planck in 1900, when he was trying to solve a problem involving how hot objects radiate energy. 5 years later, Albert Einstein took Planck's idea further and proposed that light itself comes in these discrete packets, these quanta of energy. Einstein used this idea to explain the photoelectric effect, the observation that light can knock electrons out of a metal surface, but only if the light's frequency is high enough. It didn't matter how bright the light was. If the frequency was too low, no electrons were released. This only made sense if light came in individual packets, each carrying a specific amount of energy determined by frequency. This discovery eventually earned Einstein the Nobel Prize in Physics in 1921. Now, here is the fact about photons that matters most tonight. Photons have no rest mass. Zero. None at all. If you could somehow isolate a single photon and place it on the most sensitive scale ever built, the scale wouldn't move. A photon is not like a grain of sand, not like a molecule of water, not like an electron or a proton. All of those things have mass. They have a measurable weight, a resistance to being pushed around, a gravitational pull, however small. A photon has none of that. It is a massless particle. It has exactly zero rest mass. And this is not an approximation or a rounding error. It is exactly zero. This seems like it should close the door on the entire question. Gravity, at least as most people understand it, it's about mass. Heavy things pull on other heavy things. The Earth has mass, so it pulls you toward it. The Sun has mass, so it holds the planets in orbit. Mass is what makes gravity work. And if photons have no mass, then they should have nothing to do with gravity. They should be gravitationally invisible, neither pulling on other objects nor being pulled by them. That was the conclusion you would have reached using Isaac Newton's framework. And for over 200 years, Newton's framework was the best physics had to offer. But photons carry something other than mass. They carry energy, and they carry momentum. A single photon of visible light carries a tiny amount of energy, roughly 2 to 3 electron volts. That's an incredibly small quantity, smaller than you can meaningfully imagine, but it is real and it is measurable. And photon momentum, despite being vanishingly small for any individual photon, is also real. It has physical consequences you can observe. Solar sails, thin reflective sheets designed to be deployed in space, accelerate because photons bounce off their surfaces and transfer momentum. Each individual photon imparts a minuscule push, but sunlight delivers trillions upon trillions of photons every second, and over time, those tiny pushes add up. Japan's Ika Rossa spacecraft demonstrated this in 2010, becoming the first vessel to navigate through space using nothing but the push of sunlight. Massless particles with real, measurable, physically consequential momentum. The momentum of a photon is not a mathematical abstraction, it is a force you can harness and ride. So light has energy, light has momentum, but light has no rest mass. Remember this combination because it is the foundation of everything we're about to discover. To understand why it matters, we need to leave photons behind for a moment and talk about gravity. Because our understanding of gravity has undergone a complete revolution in the past century. And that revolution is the reason light and gravity are connected at all. For most of human history, gravity was simply a fact of life with no real explanation. Things fell. Heavier things seemed to fall the same way lighter things did. Nobody knew why. Then, in 1687, Isaac Newton published his law of universal gravitation, and everything changed. Newton's insight was breathtaking in its simplicity. Every object with mass attracts every other object with mass. The strength of the attraction depends on two things: how much mass the objects have and how far apart they are. More mass means a stronger pull. Greater distance means a weaker pull. This single, elegant idea explained an astonishing range of phenomena. It explained why objects fall to the ground. It explained why the moon orbits the Earth. It explained why the Earth orbits the Sun. It predicted the motion of comets and the timing of eclipses. It was one of the most powerful ideas in the entire history of science, and it dominated physics for more than 2 centuries. Under Newton's picture, gravity is a force that acts between masses. Mass produces gravity, and mass responds to gravity. This is clean and intuitive. It matches our everyday experience. Heavy things are harder to move, and they seem to create more gravitational pull. Newton's law worked so well that for over 200 years, nobody seriously questioned it. Scientists used it to predict planetary orbits, to discover new planets, even to send spacecraft to the moon. It felt complete, but there were cracks. Newton himself was troubled by one feature of his own theory. Gravity in his framework acted instantaneously across any distance. If the sun suddenly vanished, Newton's equations said the Earth would immediately stop orbiting, even though the sun is over 150 million kilometers away. The gravitational effect would be felt instantly, with no delay. Newton knew this didn't make sense. He called it action at a distance and found it deeply unsatisfying. But he had no better explanation, so the problem went unresolved for centuries. Then, in 1905, Albert Einstein published his theory of special relativity and introduced the most famous equation in all of science: E equals mc squared. Energy equals mass times the speed of light squared. This equation is often presented as a way to calculate how much energy you can extract from a given amount of mass, and it is that. The speed of light squared is an enormous number, roughly 9 times 10 to the 16th in metric units. This means that even a tiny amount of mass contains a staggering amount of energy. A single kilogram of matter, if converted entirely to energy, would release roughly 90 quadrillion joules, enough to power a city for years. But E equals mc squared says something far deeper than just how to build bombs or power plants. It reveals a fundamental truth about the nature of reality. Mass and energy are not different things. They are two expressions of the same underlying quantity. They are interchangeable, equivalent. Mass is a form of energy. Energy has an equivalent mass. They're two sides of the same coin. And this has profound consequences for how we think about gravity. Think about what this means for photons. A photon has no rest mass. That remains absolutely true. But a photon carries energy, and energy is equivalent to mass. So that the energy of a photon has gravitational significance, even though the photon itself is massless. This doesn't mean the photon secretly has mass hidden inside it. It means something subtler and more profound. It means that the energy the photon carries interacts with the gravitational fabric of the universe in the same way that mass does. Energy and mass are the same thing as far as gravity is concerned. Here is a thought experiment that makes this concrete. Imagine you have a perfectly sealed box with perfectly reflective interior walls. The box is sitting on a scale and you've noted its weight. Now, you fill the box with an enormous number of photons, light bouncing back and forth inside, trapped by the reflective walls. Weigh the box again. It weighs more. Not because the photons have mass, but because the energy of those photons contributes to the total energy of the system. And that total energy determines how the system interacts with gravity. The box with light in it is heavier than the empty box. The photons added energy, and energy is equivalent to mass, and mass is what a scale responds to. This is not a philosophical argument. This is measurable, testable physics. You can see this principle at work inside atoms. The mass of an atomic nucleus is slightly less than the combined mass of all the protons and neutrons that make it up. The difference is called the mass defect. Where did the missing mass go? It was converted into binding energy, the energy that holds the nucleus together. And if you could somehow add that binding energy back, the mass would return. Energy and mass are interchangeable. This is the principle that makes nuclear power possible. It is the principle that makes the sun shine. And it is the principle that connects light to gravity. But Einstein didn't stop there. In 1915, he completed his masterwork, the general theory of relativity, and this theory didn't just patch up Newton's gravity. It tore it down and rebuilt it from the ground up. In general relativity, gravity is not a force at all. It doesn't pull, it doesn't push. Instead, gravity is the curvature of space-time itself. Massive objects warp the fabric of space-time around them, creating curves and dips, and other objects follow those curves. What we perceive as gravitational attraction, the apple falling from the tree, the moon circling the Earth, is really just objects following the straightest possible paths through curved space-time. There is no force reaching across the void and pulling things together. There is only geometry. The shape of space-time tells objects how to move. And here is the point that changes everything about our story tonight. In general relativity, the thing that curves space-time is not mass alone. It is the total energy and momentum content of whatever is present. This information is encoded in a mathematical object called the stress-energy tensor. You don't need to understand the mathematics to grasp the concept. The stress-energy tensor is essentially a complete accounting of everything that can influence gravity. It includes energy density, how much energy is packed into a given volume of space. It includes momentum density, how much momentum is flowing through a region. It includes pressure, including a radiation pressure, and it includes internal stresses. All of these things contribute to the curvature of space-time. All of them are sources of gravity. Mass is included, of course. Mass is a highly concentrated form of energy, so it shows up prominently in the stress-energy tensor. A massive star dominates the local curvature of space-time primarily through its rest mass. But mass is not the only contributor. Any form of energy, any form of momentum, any form of pressure curves space-time. Light carries energy and momentum. Therefore, light curves space-time. Not because it secretly contains rest mass, not because some hidden conversion takes place, but because energy and momentum are what gravity responds to, and light has both. Let that settle in. Light, massless light, photons with zero rest mass, curves space-time. A single photon's gravitational contribution is so preposterously small that no instrument in existence could detect it. But the contribution is not zero. It exists. The equations of general relativity predict it unambiguously, and those equations have been tested against observation more rigorously than almost any theory in the history of science. Every test has confirmed them, and we have direct, large-scale evidence. The most dramatic proof that light has gravitational influence comes from the early universe. In the first roughly 50,000 years after the Big Bang, the cosmos was not dominated by matter. It was dominated by radiation, photons, light. The universe at that time was a blinding, unimaginably hot plasma, and the photons in that plasma were extraordinarily energetic, far more energetic than any photons that exist naturally today. During this period, known as the radiation-dominated era, the energy density of radiation far exceeded the energy density of all the matter in the cosmos combined. And because energy density is what drives the curvature of space-time, and therefore the expansion of the universe, it was light, not matter, that governed how the universe expanded. For tens of thousands of years, the rate at which the entire observable universe expanded was determined primarily by photons, by massless particles carrying energy. The equations of general relativity predict a specific expansion rate for a universe dominated by radiation. And that rate is different from what you get if matter dominates. The expansion slows differently. The geometry evolves differently. And when cosmologists examine the cosmic microwave background, the ancient afterglow of the Big Bang that fills every corner of space, they find patterns that match the radiation-dominated prediction with extraordinary precision. Without including the gravitational contribution of light, the models fail. They predict the wrong patterns, the wrong temperature fluctuations, the wrong distribution of matter in the early cosmos. The models only succeed when the gravity of radiation is fully accounted for. Light shaped the expansion of the universe. That is confirmed observational science. We also see the connection between light and gravity in a more local way. In 1919, the British astronomer Arthur Eddington travelled to the island of Principe off the west coast of Africa to observe a total solar eclipse. During the eclipse, he photographed stars whose light passed close to the edge of the sun on its way to Earth. He found that the stars appeared slightly displaced from their expected positions. The gravity of the sun had bent the paths of the starlight, deflecting it by about 1.75 arcseconds, exactly as Einstein's general relativity predicted, and roughly twice what a Newtonian calculation would have suggested. This observation confirmed that gravity affects light. But the relationship runs both ways. Light also affects gravity. Every photon bouncing around inside the sun, every quantum of electromagnetic energy trapped within its seething plasma, contributes to the sun's total energy content. And that total energy determines how strongly the sun curves space-time around it. The sun's gravity is not produced solely by the rest mass of its atoms. It includes contributions from the thermal motion of particles, from the nuclear binding energy in its core, and from the photons ricocheting through its interior. The sun is very slightly more gravitationally influential because the light trapped inside it. The contribution is tiny compared to rest mass, but it is real, it is predicted, and it is there. And this is where the story opens up into something extraordinary. If a single photon curves space-time, even by an immeasurably small amount, then in principle, enough photons should curve space-time by an enormous amount. Not just enough to slightly deflect a passing star's image during an eclipse. Not just enough to influence the expansion of the early universe, but enough to warp the geometry of a localized region of space so completely that nothing inside that region can get out. Because general relativity does not care what form the energy takes. It does not ask whether the energy comes from a dying star, from compressed matter, from nuclear reactions, or from pure electromagnetic radiation. Energy is energy. Space-time responds to all of it equally. And if enough energy, in any form whatsoever, is confined within a small enough region of space, space-time curves past the point of no return. The equations allow it. The physics permits it. A black hole made not from the collapse of matter, but from the concentration of pure light. And the fact that photons have no rest mass does not prevent it. Because it was never about mass, it was always about energy. So light has energy, light has momentum, and energy and momentum are what curve space-time, not mass alone. That much we've established. But knowing that a single photon has a gravitational effect, however unimaginably small, is very different from understanding how photons could ever create a black hole. The gap between those two ideas is enormous, and crossing that gap requires us to think carefully about something we don't usually think about at all. We need to think about density. Not just mass density, the kind you learn about in school when you talk about LED being denser than aluminum. We need to think about energy density. How much energy is packed into a given volume of space? Because in general relativity, energy density is what matters most. It's the single biggest contributor to local space-time curvature. And the story of light collapsing into a black hole is really the story of energy density being pushed to its absolute extreme. Let's start with something intuitive. Imagine you have a room, an ordinary room, and you fill it with warm air. That air has energy. The molecules are bouncing around, vibrating, carrying kinetic energy. The total energy in the room is real and measurable, but it's spread out over a large volume. The energy density is low. Now, imagine compressing all that air into a container the size of a shoebox. The total amount of energy hasn't changed. It's the same air, the same molecules, the same kinetic energy. But now it's packed into a much smaller space. The energy density has gone up dramatically. The molecules are crammed together, colliding more often, bouncing off the walls more violently. The pressure inside that shoebox would be extreme. This is the basic principle we need to apply to light. A photon traveling through empty space has a tiny amount of energy spread out over its path. The energy density associated with a single photon in open space is vanishingly small. It curves space-time by an amount so minuscule that no conceivable instrument could ever detect it. But what if you didn't have one photon? What if you had an inconceivably large number of photons? And what if you didn't let them spread out? What if, instead of letting all that electromagnetic energy radiate outward in every direction the way light naturally does, you forced it inward? What if you concentrated all that energy into a smaller and smaller and smaller region? The total energy stays the same, but the volume it occupies shrinks, and as the volume shrinks, the energy density rises. The more you compress the radiation into a smaller space, the more energy per unit volume you have. And the more energy per unit volume you have, the more severely that region of space curves. General relativity tells us something profound and unsettling about this process. There is no hard barrier, no wall, no physical law that says energy density cannot keep rising. You can, in principle, keep compressing electromagnetic energy into a smaller and smaller region. And as you do, the space-time curvature around that region gets steeper and steeper. At low energy densities, the curvature is negligible. Space is essentially flat. At moderate energy densities, the curvature becomes measurable but small. Light passing through the region would be deflected slightly, bent along a curved path, but it would still escape. At high energy densities, the curvature becomes severe. Light passing close to the region would be strongly deflected. Some of it might orbit the region briefly before escaping. But if you keep going, if you keep increasing the energy density, you eventually reach a threshold where the curvature becomes so extreme that no path leads outward. Every trajectory that light could follow curves back in on itself. Light can no longer escape, and at that point, you have an event horizon, a boundary in space-time beyond which nothing, not even light itself, can leave. But before we reach that extreme endpoint, something interesting happens at intermediate energy densities. Something that explored decades before the word kugelblitz entered the conversation. In the 1950s, the American physicist John Archibald Wheeler became fascinated with a question that sits right at the boundary between light and gravity. Wheeler asked whether electromagnetic radiation, concentrated in the right configuration, could hold itself together gravitationally, not collapsing into a black hole, not forming an event horizon, just orbiting itself, trapped temporarily by the curvature its own energy creates. Wheeler called these hypothetical objects geons, short for gravitational electromagnetic entities. The idea was elegant. Imagine a bundle of photons arranged so that they travel in a circular or spherical pattern, each photon following a curved path created by the combined energy of all the others. The photons would orbit each other, held in place not by any container or reflective wall, but by the gravitational curvature they themselves produce. A self-sustaining ball of light, bound by its own gravity. Wheeler worked through the mathematics and found that geons were indeed solutions to Einstein's field equations. The equations permitted them, but he also found that they were unstable. A geon would not last forever. It would slowly leak energy, losing photons that spiraled outward and escaped. Over time, the geon would evaporate, fading away as its trapped radiation gradually dispersed. A geon was not a permanent structure. It was a temporary one, a fleeting configuration of light that gravity could almost hold together, but not quite. This might seem like a failure, but it was actually a crucial stepping stone. Wheeler's geons demonstrated that light could interact with its own gravitational field in physically meaningful ways. Radiation was not gravitationally inert. It could curve space-time enough to influence its own motion, even if it couldn't quite hold itself together permanently. The Geon was proof of concept. It showed that the gravitational self-interaction of light was real, not just a mathematical curiosity. And it raised an obvious question. If light can almost hold itself together gravitationally, what happens if you push harder? What happens if you pack in more energy? Enough energy that the gravitational curvature becomes so severe that the photons can't escape at all? The answer, of course, is a kugelblitz. The Geon is the gentle prelude. The kugelblitz is the dramatic conclusion. The threshold between these two regimes, between a Geon that slowly leaks and a kugelblitz that seals shut forever, is precisely defined by the mathematics of general relativity. For any given amount of energy, there is a specific radius. If that energy is entirely confined within a sphere of that radius, an event horizon forms. This critical radius is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first calculated it in 1916, barely a year after Einstein published the general theory of relativity. Karl Schwarzschild's story is remarkable and tragic. He derived his solution while serving in the German army on the Russian front during World War I, working out the mathematics in the trenches under artillery fire. He sent his calculations to Einstein, who presented them to the Prussian Academy of Sciences. Schwarzschild died just months later from a disease he contracted on the front. He never lived to see the extraordinary implications of his work unfold over the following century. The Schwarzschild radius itself is surprisingly simple to calculate. For any quantity of energy, you convert that energy to its equivalent mass using Einstein's famous equation E equals mc squared, rearranged so that mass equals energy divided by c squared. Then you plug the equivalent mass into the formula for the Schwarzschild radius, which is 2 times the gravitational constant times the mass divided by the speed of light squared. The result is the radius within which that energy must be confined to form an event horizon. What makes this formula so important for our story is what it doesn't say. It doesn't say the energy must come from matter. It doesn't require atoms or electrons or protons or any kind of ordinary substance. The formula asks only one question: how much energy is there? That's it. The energy could come from a collapsing star. It could come from compressed iron and hydrogen. It could come from dark matter or exotic particles or anything else. And crucially, it could come from photons, from pure electromagnetic radiation, from light. The formula does not distinguish. As far as the Schwarzschild radius is concerned, energy is energy. Let's run through some numbers to understand the scale. Start with something familiar. Our sun has a mass of about 2 times 10 to the 30th kilograms. If you could compress the entire sun into a sphere with a radius of about 3 kilometers, roughly the distance of a short jog, it would become a black hole. 3 kilometers. The sun, which has a diameter of about 864,000 miles, would need to be squeezed down to a ball 6 kilometers across. That's the Schwarzschild radius for one solar mass worth of energy. Now, the sun is made of matter. It's made of hydrogen and helium and trace amounts of heavier elements. But imagine, purely as a thought experiment, that instead of compressing matter, you wanted to create the same event horizon using pure light. You would need photons carrying the same total energy as the rest mass energy of the sun. How much energy is that? Using E equals mc squared, The rest mass energy of the Sun is approximately 1.8 times 10 to the 47th joules. That is an almost incomprehensible number. Written out, it would be a 1 followed by 47 zeros worth of joules. But let's try to put it in perspective anyway. The total energy output of the Sun, everything it radiates, all the light and heat and ultraviolet and X-rays combined, is about 3.8 times 10 to the 26th watts. That means the Sun radiates roughly 3.8 times 10 to the 26th joules of energy every second. This is already an unimaginable amount of energy. In 1 second, the Sun releases more energy than all of human civilization has consumed in its entire history. But even at this staggering rate, how long would the Sun need to shine in order to radiate a total amount of energy equal to its own rest mass energy? The answer is roughly 15 trillion years. That is more than 1,000 times the current age of the universe. 15 trillion years of continuous output at the Sun's full luminosity, every photon captured and none lost, before you accumulated enough electromagnetic energy to match the rest mass energy of the Sun. And that's assuming you could somehow collect and concentrate every single photon the Sun emits, in every direction, with perfect efficiency. In reality, the Sun radiates outward in a sphere. Its energy spreads across the entire sky. Capturing all of it would require a shell surrounding the Sun at every angle, intercepting every last photon. This hypothetical structure is sometimes called a Dyson sphere, named after the physicist Freeman Dyson, who proposed the concept in 1960. Dyson's idea was not science fiction, at least not entirely. He was thinking about the energy needs of advanced civilizations. A civilization that had existed for millions of years and expanded across its solar system would eventually need more energy than any single planet could provide. The only way to capture the full output of a star would be to surround it completely. A Dyson sphere, or more realistically a swarm of orbiting solar collectors, would intercept every photon the star emits. The total energy available would be the star's entire luminosity, roughly 3.8 times 10 to the 26 watts for a Sun-like star. This idea connects to a framework proposed by the Soviet astronomer Nikolai Kardashev in 1964. Kardashev suggested classifying civilizations by how much energy they could harness. A Type 1 civilization controls the energy resources of its home planet, roughly 10 to the 16th watts. Humanity is not yet a Type 1 civilization. We use only a fraction of the energy that reaches Earth from the Sun. A Type 2 civilization harnesses the total energy output of its star, roughly 10 to the 26th watts. This is the Dyson sphere level. A Type 3 civilization commands the energy of an entire galaxy, roughly 10 to the 36th watts. The Kardashev scale helps us understand just how far beyond our reach a kugelblitz truly is. Even a full Type 2 civilization, one that had built a complete Dyson sphere and was capturing every photon its star emitted, would need to collect energy for roughly 15 trillion years before it had enough for a solar mass kugelblitz. And that civilization would then need to focus all of that stored energy inward onto a target 6 kilometers across, with every photon arriving simultaneously. A Type 2 civilization represents a level of technological advancement so far beyond anything humanity has achieved that it borders on the fantastical. And even a Type 2 civilization would find a kugelblitz essentially impossible. The energy timescale alone, trillions of years of perfect collection, places it beyond any reasonable engineering project. You might need a Type 3 civilization, one that commands the energy of an entire galaxy, to even begin contemplating the necessary energy budget on a practical timescale. And even then, the focusing problem remains unsolved. But even if you built a Dyson sphere, even if you captured every photon the sun emitted for 15 trillion years, you still wouldn't have a black hole. You'd have the right amount of energy, but the energy would need to be focused inward, concentrated into a sphere no wider than 6 kilometers across. Every photon arriving simultaneously from every direction, converging on a single point in space. The precision required is beyond anything that words like difficult or challenging can convey. We are talking about focusing the entire luminous output of a star, collected over trillions of years, into a volume smaller than a large city, with every photon arriving at the same moment. And this brings us to a critical point. The Schwarzschild radius gets smaller as the energy decreases. If you want to make a smaller black hole using less energy, you need to concentrate that smaller amount of energy into an even smaller volume. The relationship is linear. Half the energy means half the Schwarzschild radius. 1,000th of the energy means 1,000th of the Schwarzschild radius. If you wanted to create a black hole with the mass energy equivalent of Mount Everest, roughly 800 trillion kilograms, you'd need to confine the corresponding energy within a Schwarzschild radius of about 1.2 times 10 to the negative 12 meters. That is smaller than an atom, smaller than a proton. You would need to pack a mountain's worth of energy into a volume smaller than the nucleus of an atom. The numbers are absurd, and they only get more absurd as you consider smaller amounts of energy. This is why the concept remains theoretical. It isn't that the physics is wrong. The physics is solid. General relativity has been verified by more than a century of precision experiments. From the bending of starlight during eclipses, to the detection of gravitational waves from merging black holes in 2015, the equations permit it, they describe it clearly. But the engineering, the practical reality of actually concentrating that much electromagnetic energy into that small a space is so far beyond current or foreseeable technology that it barely qualifies as engineering. It's closer to fantasy. But physicists love thought experiments, and this one has earned a name. A black hole formed not from the gravitational collapse of matter, but from the concentration of pure electromagnetic radiation is called a kugelblitz. The word is German. It translates roughly to ball lightning, which is a beautifully evocative name, even if it's not quite accurate. A kugelblitz has nothing to do with actual ball lightning, the mysterious atmospheric phenomenon that sometimes appears during thunderstorms. The name was adopted because it captures the image of a sphere of concentrated energy, a ball of light so intense that it collapses under its own gravitational influence. Wheeler, whose geons had already demonstrated that light could gravitationally interact with itself, was among the first to seriously explore the kugelblitz concept. Wheeler, who also coined the term black hole, spent much of his career thinking about the extreme limits of general relativity. He was interested in what happened when you pushed the equations to their breaking point. The geon was light almost trapping itself. The kugelblitz was light succeeding. Could pure energy with no rest mass whatsoever form a gravitational singularity? Wheeler showed that the equations said yes. There was no mathematical prohibition. If the energy density of electromagnetic radiation in a confined region exceeds the threshold defined by the Schwarzschild radius for that energy, an event horizon forms. The radiation becomes trapped behind its own gravitational barrier. The G on leaks, the kugelblitz seals shut. The difference is only the amount of energy involved. What makes the kugelblitz concept so profound is not just that it's possible in theory, it's what it tells us about the nature of gravity itself. In Newton's universe, this could never happen. Newtonian gravity responds only to mass. No mass, no gravity. Period. A universe full of light and nothing else would have zero gravity in Newton's framework. But Einstein's universe is different. Einstein showed us that gravity is not about mass. It is about energy and momentum and pressure and stress. It is about the full content of the stress-energy tensor. And light contributes to all of those quantities. Light has energy. Light has momentum. Light exerts radiation pressure. All of these things curve spacetime. And if enough of them are concentrated in one place, spacetime curves past the point of no return. And here is something crucial that many people misunderstand. The light does not need to slow down. It does not need to stop moving. It does not need to convert into matter or transform into something else before the collapse occurs. The photons continue traveling at the speed of light, 300,000 kilometers per second, right up until the event horizon forms. There is no moment where the photons are held in place by some force the way matter might be compressed by gravity in a collapsing star. Instead, the photons continue moving at full speed, but the geometry of space around them changes. The paths they follow, which in flat space-time would carry them outward and away, become curved inward. The exit routes close. The space-time itself reshapes so that every possible direction, even for something moving at the speed of light, leads back inward rather than outward. The photons are not slowed, they are enclosed. This is one of the most important distinctions between a matter-based black hole and a kugelblitz. In a conventional black hole, a massive star runs out of fuel and the core collapses under its own gravity. Matter is physically compressed, crushed together with unimaginable force. The density rises until an event horizon forms. In a kugelblitz, there is no compression in the mechanical sense. Radiation is not being squeezed the way matter is squeezed. Instead, an enormous quantity of energy is being directed inward from all directions, converging on a single region. The energy density in that region spikes, space-time curves in response, and the event horizon seals shut around the radiation. The mechanism is geometric, not mechanical. It is space-time itself that does the trapping, not physical pressure. And once the event horizon forms, something remarkable happens. The black hole that results is defined entirely by its total energy content, not by the nature of whatever supplied that energy. This is a consequence of a principle in black hole physics known informally as the no-hair idea. We'll explore this in more detail shortly, but the essential point is this. A black hole has only a handful of measurable properties: its total mass energy, its electric charge, and its angular momentum, which is how fast it's spinning. That's it. Nothing else about the black hole's origin survives. A black hole formed from a collapsing iron star and a kugelblitz formed from pure concentrated light would be completely, perfectly, fundamentally indistinguishable from each other if they had the same mass energy, charge, and spin. There would be no observation, no experiment, no measurement of any kind that could tell you which one came from matter and which came from light. The universe erases the origin story. All that remains is the geometry. This means that the energy of the photons, once trapped behind the event horizon, becomes the mass of the black hole, not because the photons turned into matter, not because some mysterious conversion happened inside the event horizon, but because mass, in the context of general relativity, is just a way of quantifying the total energy content of a gravitationally bound system as seen from the outside. The external gravitational field of the black hole is determined by how much energy is inside the event horizon, and it does not matter what form that energy takes. A kilogram of iron behind an event horizon and a kilogram equivalent of photon energy behind an event horizon produce the same spacetime curvature outside. They are the same mass, gravitationally speaking. This is the ultimate expression of Einstein's E equals mc squared. Mass is energy. Energy is mass. And gravity does not care which form it takes. Let me give you one more way to think about the energy requirements, because the numbers are so extreme that they deserve repetition from a different angle. Imagine the most powerful laser humanity has ever built. The National Ignition Facility in the United States uses 192 laser beams converging simultaneously on a target the size of a pencil eraser. The total energy delivered in a single pulse, it was about 2 megajoules. 2 million joules. That sounds impressive. And in terms of human engineering, it is impressive. It represents decades of scientific development and billions of dollars of investment. But 2 megajoules, converted to mass energy using E equals mc squared, corresponds to a mass of roughly 2 times 10 to the negative 11 kilograms, 20 trillionths of a kilogram, a fraction of the weight of a single grain of sand. The Schwarzschild radius for that amount of energy is approximately 3 times 10 to the negative 38 meters. That is not just small, that is smaller than the Planck length. The scale at which our current understanding of physics itself breaks down. You could fire every laser humanity has ever built, every laser that exists on Earth today, simultaneously into a single point, and the combined energy would still be so far below the threshold for black hole formation that the comparison is laughable. Not just difficult, not just impractical, laughable. To form a kugelblitz with a Schwarzschild radius of even 1 Planck length, the smallest meaningful length scale in known physics, you would need an energy of roughly 10 to the 9th joules, a billion joules, concentrated into a region 10 to the negative 35 meters across. A billion joules is achievable in principle. A single lightning bolt carries about a billion joules, but concentrating that energy into a sphere 10 to the negative 35 meters across is not achievable. Not with current technology, not with foreseeable technology, not with any technology that operates within the physical frameworks we currently understand. The focusing requirement is the real barrier, not the raw energy. You don't just need a lot of light. You need all of that light to converge simultaneously from every direction into a target smaller than anything that has ever been measured or observed. And the numbers only get more extreme if you want a bigger black hole. For a kugelblitz with a Schwarzschild radius of 1 meter, roughly the size of a beach ball, you would need an energy equivalent to roughly 6.7 times 10 to the 26 kilograms. That is comparable to the entire mass of the planet Saturn, compressed into a sphere you could wrap your arms around, focused into that sphere 1 meter across. The entire concept sits in a strange twilight zone between mathematical legitimacy and physical absurdity. The equations allow it. They even describe it cleanly and elegantly. but the reality of achieving it seems so far beyond human capability. So far beyond even the capability of any known natural process, that it exists almost purely as a theoretical exercise, a way of testing the limits of general relativity, a way of asking what the laws of physics permit when pushed to their most extreme logical conclusions. And yet, the concept is important, not because anyone expects to build a kugelblitz, but because it reveals something deep about the nature of gravity and the nature of space-time. It shows us that gravity is not about matter, it is about energy. Any kind of energy, focused tightly enough, arranged densely enough, confined within a small enough volume, pure light, pure massless electromagnetic radiation can do what we normally associate only with the densest matter in the cosmos. It can create a black hole, not despite being massless, but precisely because it carries energy. And in Einstein's universe, energy is all that gravity needs. So we know that general relativity allows it. We know that if an enormous quantity of electromagnetic radiation is concentrated into a region smaller than its corresponding Schwarzschild radius, an event horizon will form. We know that the equations draw no distinction between energy from matter and energy from light. The mathematics is clean, the principle is established, but mathematics describes the endpoint. It tells us that a black hole forms. What it doesn't immediately tell us, at least not without careful thought, is what the process would actually look like. What would an observer standing at a safe distance actually see if a kugelblitz were forming before their eyes? What would happen to the light as space-time curved more and more severely? And once the event horizon sealed shut, what will be left behind? Those questions lead us into some of the strangest territory in all of physics, and the answers are both beautiful and deeply unsettling. Let's set the stage. Imagine, purely as a thought experiment, that some impossibly advanced civilization has found a way to produce and direct a staggering quantity of electromagnetic radiation inward from every direction simultaneously. We're not worrying about the engineering right now. We covered the absurdity of the energy requirements already. For now, let's just assume the energy is there, and it's being focused. Photons from every angle are converging on a single point in space. A target region so small, it makes an atom look like a continent. And you're watching from a safe distance, far enough away that the gravitational effects haven't reached you yet. What do you see? At first, you see light. Blinding, intense, overwhelming light. The converging radiation would be visible in whatever portion of the electromagnetic spectrum it occupied. If the photons were in the visible range, you would see an impossibly brilliant sphere of luminosity, a point in space glowing with a ferocity that dwarfs anything in nature. The energy density in that region would already be extraordinary, far exceeding what exists inside any star, but space-time would still be only mildly curved. The photons are converging, but they haven't yet been confined tightly enough for the curvature to become extreme. Light from that region can still reach you. Information can still escape. But as more energy pours in, as the radiation density climbs higher and higher, something begins to change. Not in the light itself, but in the space around it. Space-time is curving more steeply now. The geometry of the region is warping. And this warping has a visible, measurable consequence. It's called gravitational redshift. Gravitational redshift is one of the most elegant predictions of general relativity, and it has been confirmed experimentally many times. The idea is simple but profound. When light climbs out of a gravitational field, it loses energy. Not because something absorbs part of its energy along the way, but because the fabric of space-time itself stretches the light as it climbs. The wavelength gets longer. And since longer wavelengths correspond to lower energies and redder colors, the light shifts toward the red end of the spectrum. It's the same basic idea as the Doppler effect you hear when an ambulance drives past you, except instead of motion through space causing the frequency shift, it's the curvature of space-time itself. This effect is not just theoretical, it was confirmed in a landmark experiment in 1959 by two physicists at Harvard University, Robert Pound and Glenn Rebka. Their experiment was beautifully simple in concept, though extraordinarily difficult in practice. They set up a source of gamma rays at the top of a tower in the Jefferson Physical Laboratory, about 22.5 meters above the ground. At the bottom of the tower, they placed a detector. The gamma rays were emitted at a very precise frequency, and the detector was tuned to measure that frequency with extreme accuracy. What Pound and Rebka found was that the gamma rays arriving at the bottom of the tower had a very slightly higher frequency than the ones emitted at the top. The light had fallen through Earth's gravitational field, gaining energy as it descended, and that energy gain manifested as a blue shift, a shift toward higher frequencies. The effect was tiny, a fractional change of about 2.5 parts in 10 to the 15th, but it was real, measurable, and it matched Einstein's prediction exactly. When they reversed the experiment, sending gamma rays upward from the bottom of the tower to the top, they found the corresponding redshift. Light climbing out of a gravitational field lost energy. Light, falling in, gained energy. The Pound-Rebka experiment was a quiet triumph. It didn't make headlines the way a rocket launch or a particle discovery might, but it confirmed one of the most fundamental predictions of general relativity in a controlled laboratory setting, right here on Earth, using a tower barely taller than a 2-story building. If gravity can measurably shift the frequency of a photon over a distance of 22 meters in Earth's weak gravitational field, imagine what happens near a forming kugelblitz, where the gravitational field is not weak at all but approaching the most extreme conditions space-time can produce. Near a forming event horizon, gravitational redshift becomes extreme. As the energy density in the converging region increases, and space-time curves more and more severely, the light escaping from that region shifts further and further toward the red. Blue light becomes green, green becomes yellow, yellow becomes orange, orange becomes red, red becomes infrared, invisible to human eyes. The glowing sphere doesn't just dim, it changes color, sliding down the spectrum toward longer and longer wavelengths, and it gets dimmer too. Not just because the light is being redshifted out of the visible range, but because of another effect called gravitational time dilation. Near a strongly curved region of space-time, time itself runs more slowly relative to a distant observer. This is the same phenomenon confirmed by the Pound-Rebka experiment, expressed differently. As the energy density approaches the threshold for event horizon formation, time in the converging region slows dramatically from your perspective. Photons escaping from that region arrive at your eyes less and less frequently. The light doesn't just redshift, it also becomes stretched out in time. Flashes of light that were emitted a microsecond apart at the source might arrive at your eyes seconds or minutes apart by the time the curvature is severe enough The combined effect is haunting. From your safe distance, you watch the brilliant sphere of converging radiation gradually dim and redden. It slides from blinding white to yellow, from yellow to deep red, from red to infrared, from infrared to microwave, from microwave to radio frequencies, each transition carrying less energy and less information. The sphere seems to freeze, not because anything has stopped moving, but because the time dilation is so extreme that processes near the forming horizon appear to take longer and longer from your vantage point. The final moments before the event horizon seals shut are stretched out asymptotically. From a mathematical perspective, you never actually see the horizon form. The last photons to escape are so profoundly redshifted and so enormously spread out in time that they become undetectable. The sphere fades from view, dimming to blackness over a finite period as far as your instruments are concerned, but technically emitting those final, impossibly faint photons forever. And then, silence. Darkness. Where there was once a blinding sphere of converging light, there is now nothing visible at all. Just a region of space that light enters but does not leave. An event horizon has formed. The kugelblitz is born. Now, what exactly exists behind that event horizon? This is where the physics becomes genuinely strange, and where the nature of a kugelblitz becomes indistinguishable from any other black hole. Because the answer, as far as the external universe is concerned, is that it doesn't matter what's behind the event horizon. The universe outside cannot tell. This principle is captured by one of the most remarkable results in black hole physics. A result that the physicist John Archibald Wheeler summarized in one of the most memorable phrases in all of science. Black holes have no hair. The no-hair idea, sometimes stated more formally as the no-hair theorem, says that a black hole in a settled, stable state is completely described by exactly three numbers: its total mass energy, its total electric charge, and its total angular momentum. That's it. Three numbers. Nothing else about the black hole's history. Nothing about what formed it, nothing about what fell into it, nothing about the internal arrangement of matter or energy behind the horizon is accessible to the outside universe. A black hole formed from a collapsing star made of iron and silicon carries no memory of iron and silicon. A black hole formed from collapsing hydrogen carries no memory of hydrogen. And a kugelblitz formed entirely from concentrated electromagnetic radiation carries no memory of photons. Once the event horizon forms, the origin story is erased. This means something extraordinary for our thought experiment. The kugelblitz that just formed in front of you, the black hole made of pure trapped light, is gravitationally and observationally identical to any other black hole of the same mass, charge, and spin. If someone handed you a black hole and asked whether it came from a dying star or from focused radiation, you could not answer. No telescope, no detector, no instrument of any kind, no matter how advanced, could distinguish between the two. The event horizon looks the same. The gravitational field looks the same. The way the black hole bends light around it, the way it warps space-time in its vicinity, all of it is identical. The universe treats them as the same object because in every physically meaningful sense, they are the same object. This is the ultimate expression of the equivalence of mass and energy. Behind one event horizon sits compressed stellar matter, the remnants of a star that fused hydrogen for billions of years before collapsing. Behind another sits nothing but trapped electromagnetic radiation, photons that never had rest mass at any point in their existence. Both event horizons are identical from the outside. Because mass and energy are not just interchangeable in abstract equations, they are indistinguishable in their gravitational consequences. Gravity genuinely does not care what form the energy takes. It only cares how much there is. We know of real black holes in the universe, stellar mass black holes with masses of roughly 5 to 100 times the mass of our Sun, formed from the collapsed cores of massive stars. Supermassive black holes with masses of millions to billions of solar masses, sitting at the centers of galaxies. Sagittarius A star, the supermassive black hole at the center of the Milky Way, has a mass of about 4 million times the mass of our Sun. The black hole at the center of M87, the one imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses. All of these are thought to have formed through matter-based processes. Stars collapsing, gas accreting, galaxies merging. None of them are believed to be kugelblitzen. But if one of them were, if some unknown process had created a kugelblitz with the same mass as Sagittarius A star, we would have no way of knowing. The black hole would behave identically. It would orbit identically. Stars near it would move on the same trajectories. Light would bend around it in the same way. The image taken by the Event Horizon Telescope would look the same. The origin is hidden forever behind the event horizon. But there is one way that the story of a kugelblitz differs from the story of a large astrophysical black hole, and it has to do with what happens after the black hole forms. Because black holes, despite their fearsome reputation, are not eternal. They evaporate, and the rate at which they evaporate depends critically on their size. Understanding why requires one of the most surprising discoveries in the history of theoretical physics. A discovery that began with a bold conjecture about the relationship between black holes and thermodynamics. In 1972, a young Israeli-American physicist named Jacob Bekenstein proposed something that most of the physics community considered absurd. He claimed that black holes have entropy. Entropy is a measure of disorder, of the number of possible microscopic arrangements a system can have. A hot gas has high entropy because the molecules can be arranged in an enormous number of ways. A crystal has low entropy because the atoms are locked into an orderly structure. Entropy is also deeply connected to information. The more entropy a system has, the more information is required to describe its exact microscopic state. Bekenstein argued that a black hole must have entropy because of the no-hair theorem itself. When matter falls into a black hole, all the detailed information about that matter, its composition, its temperature, the arrangement of its atoms, is lost to the outside universe. The only thing that changes is the black hole's mass, charge, and spin. All that detailed information seems to vanish. But the second law of thermodynamics says that the total entropy of a closed system can never decrease. If matter with high entropy falls into a black hole and the entropy simply disappears, the second law would be violated. The total entropy of the universe would have gone down. Bekenstein's solution was elegant. The black hole itself must carry entropy, and that entropy must increase whenever anything falls in. Specifically, Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon, not the volume, the area. This was strange because in every other physical system, entropy scales with volume. A box of gas has entropy proportional to its volume, but a black hole has entropy proportional to its surface area. This was one of the first hints that black hole physics is deeply connected to the physics of surfaces and boundaries, an idea that would eventually evolve into the holographic principle, one of the most profound conjectures in modern theoretical physics. But here was the problem. If a black hole has entropy, and entropy is related to temperature, then a black hole must have a temperature. And if a black hole has a temperature, it must radiate. An object with a temperature above absolute zero emits thermal radiation. That's a fundamental law of physics. But a black hole is supposed to be black. Nothing escapes from it. How can it radiate? This is where Stephen Hawking entered the story. Hawking initially set out to prove Bekenstein wrong. He thought the idea of black hole entropy was flawed, and he wanted to demonstrate the flaw rigorously. Instead, working through the mathematics of quantum field theory in curved spacetime, Hawking discovered that Bekenstein was right, and the implications were even more dramatic than Bekenstein had imagined. In 1974, Hawking showed that black holes do radiate. The radiation comes from the boundary of the event horizon, from the extreme curvature of spacetime at its edge. This radiation, now called Hawking radiation, is a consequence of the quantum nature of empty space. To understand why, you need to know something about the vacuum. In quantum mechanics, empty space is not truly empty. It seethes with activity. Pairs of virtual particles are constantly flickering into and out of existence. A particle and its antiparticle appearing together for a fantastically brief instant, and then annihilating each other before they can be observed. This happens everywhere in the universe, all the time, in every cubic centimeter of space. Under normal circumstances, these virtual particles come and go without any lasting effect. But near the event horizon of a black hole, something different can happen. A pair of virtual particles can appear right at the edge of the horizon, and before they annihilate each other, one of them falls in while the other escapes. The particle that escapes carries energy away from the black hole. The particle that falls in effectively contributes negative energy to the black hole's interior, reducing its total mass energy. The result is that the black hole loses energy. It radiates. It shrinks. Over immense timescales, it evaporates. Hawking showed that this radiation has a specific temperature, and that temperature depends on the mass of the black hole. The relationship is inverse and dramatic. The more massive the black hole, the lower its Hawking temperature. The less massive it is, the higher its temperature. This means that black holes of different sizes live dramatically different lives after they form. And for a kugelblitz, this has profound consequences, because the size of the black hole you create depends entirely on how much energy you put in. Different energy budgets produce different kugelblitzen, and those different kugelblitzen have wildly different fates. Let's walk through the possibilities, starting large and working our way down. This comparison will make the relationship between size, temperature, and lifetime vivid. Imagine a kugelblitz with the mass of the Earth, roughly 6 times 10 to the 24 kilograms. This is an enormous amount of energy, far beyond anything we discussed in terms of practical feasibility. But let's set that aside and think about the object itself. An Earth mass black hole would have a Schwarzschild radius of roughly 9 millimeters, less than a centimeter. The entire mass of the Earth compressed into a sphere smaller than a marble. Its Hawking temperature would be about 2/100ths of a Kelvin. Extraordinarily cold. Far colder than the cosmic microwave background, which fills the universe at a temperature of about 2.7 Kelvin. This black hole would radiate so slowly that its evaporation timescale would be roughly 5 times 10 to the 50th years. That is a number with 50 zeros after it. The universe is only about 13.8 billion years old. This kugelblitz would outlast every star, every galaxy, every large-scale structure in the cosmos. It would persist through the era when all stars have burned out, through the era when all ordinary matter has decayed, sitting quietly in the void, radiating almost imperceptibly, losing mass photon by photon over timescales that make the current age of the universe look like the blink of an eye. Now consider a smaller kugelblitz, one with the mass of the moon, roughly 7 times 10 to the 22 kilograms. Its Schwarzschild radius would be about 1/10 of a millimeter, barely visible to the naked eye. Its Hawking temperature would be correspondingly higher, about 1.7 Kelvin. Still incredibly cold, just below the temperature of the cosmic microwave background, but far warmer than the Earth mass black hole. Its evaporation timescale would be shorter too, roughly 10 to the 45th years. Still incomprehensibly long by any human standard, but noticeably shorter in the cosmic scheme of things. This black hole would also outlast the stars, but by a somewhat smaller margin. Drop down to a kugelblitz with a mass of roughly 100 billion kilograms, 10 to the 11th kilograms, comparable to a small asteroid. Now the Schwarzschild radius shrinks to about 10 to the negative 16 meters, far smaller than a proton. The Hawking temperature rises to about 1 trillion Kelvin, hotter than any stellar core. This black hole would be intensely hot. And because it's hot, it would radiate quickly. Its evaporation timescale would be on the order of a few billion years. That is comparable to the current age of the universe. A kugelblitz of this mass created at the time of the Big Bang would be approaching the end of its life right about now. It will be growing hotter and brighter, radiating more and more furiously as it shrinks, approaching the explosive finale of its evaporation. Shrink the energy further. A kugelblitz with the mass of a small building, maybe 10 to the 6 kilograms, 1,000,000 kilograms. The Schwarzschild radius is now about 10 to the negative 21 meters, far smaller than any atomic nucleus. The Hawking temperature soars to roughly 10 to the 17th Kelvin, comparable to the temperatures that existed in the universe a tiny fraction of a second after the Big Bang. The evaporation timescale drops to mere seconds. This kugelblitz would form, blaze with radiation hotter than any star, and vanish in a flash, all within the time it takes you to draw a breath. And at the extreme end, a kugelblitz with the Planck mass, about 22 micrograms, the smallest black hole that our current physics can meaningfully describe. The Schwarzschild radius equals the Planck length, roughly 10 to the negative 35 meters. The Hawking temperature reaches approximately 10 to the 32nd Kelvin, a temperature so extreme it matches the conditions that existed at the very earliest moments after the Big Bang, when the universe was younger than 10 to the negative 43 seconds old. And the evaporation timescale is 1 Planck time, roughly 5.4 times 10 to the negative 44 seconds. The black hole forms and detonates essentially simultaneously. It exists for the smallest meaningful interval of time in known physics, then returns all its energy to the universe in a single explosive pulse of Hawking radiation. The pattern is clear and dramatic. Larger kugelblitzen are cold, dim, and nearly eternal. Smaller ones are hot, brilliant, and fleeting. The relationship between mass and lifetime is not linear. It's cubic. Cut the mass in half and the evaporation time drops by a factor of 8. Cut the mass by a factor of 10 and the lifetime drops by a factor of 1,000. This means that the kugelblitzen most likely to be produced in any conceivable scenario, the smallest ones created with the least energy, are precisely the ones that would vanish almost instantly, detonating in flashes of radiation too brief and too energetic for any conceivable detector to capture. The energy is not lost. Conservation of energy is one of the most fundamental principles in physics, and it holds here. The energy you put in is the energy that comes back out, but it comes back out in a different form. The original radiation, the photons you focused inward, had specific frequencies, specific polarizations, specific directions. The Hawking radiation that comes out is thermal. It's random. It carries no information about what went in. It's just heat, pure and formless, spread across the electromagnetic spectrum according to the black hole's temperature. The organized energy you put in has been scrambled into disorganized thermal radiation. The information about the original photons is effectively erased. This scrambling of information is connected to one of the deepest unsolved problems in theoretical physics, the black hole information paradox. Quantum mechanics insists that information cannot be destroyed. This principle is called unitarity, and it is one of the foundational pillars of quantum theory. Unitarity means that the equations governing quantum systems are reversible. Given the final state of a system and the laws of physics, you could in principle reconstruct the initial state. No information is ever truly lost. Every physical process can, at least mathematically, be run backward. But Hawking radiation appears to violate this principle. The radiation emerging from a black hole is thermal, random, characterized by nothing but the black hole's temperature. It carries no fingerprints of what fell in. If a black hole forms from a collapsing star made of iron, and another forms from a collapsing cloud of hydrogen, both eventually evaporate, and the Hawking radiation from both looks exactly the same, assuming they had the same initial mass. The detailed information about iron atoms versus hydrogen molecules has been erased. The final state does not encode the initial state. The process is irreversible, at least apparently. And that contradicts unitarity. This contradiction alarmed physicists deeply. If black holes truly destroy information, then quantum mechanics is incomplete or wrong in some fundamental way. The stakes could not be higher. Quantum mechanics is not some marginal theory that might be quietly corrected. It is the foundation of all modern physics, from semiconductors to nuclear reactors to the behavior of atoms and molecules. If unitarity fails, the consequences ripple through all of physics. The debate that followed became known informally as the Black Hole War. On one side stood Hawking, who argued that black holes genuinely destroy information. This was a radical position, but Hawking was not easily dismissed. He had discovered Hawking radiation, and he understood the physics of black holes as well as anyone alive. On the other side stood physicists like Leonard Susskind and Gerard 't Hooft, who argued that information must be preserved because unitarity is too fundamental to abandon. Susskind in particular spent decades developing arguments for why information must survive, even if we don't understand the mechanism. The debate raged for over 25 years. It consumed some of the best minds in theoretical physics. New ideas emerged, including the holographic principle, which suggests that all the information about what falls into a black hole is somehow encoded on its event horizon, spread across its surface like words written on the skin of a balloon. The information isn't inside the black hole, it's on the boundary. This idea, while strange, offered a way to preserve unitarité without requiring information to escape from behind the event horizon. In 2004, Hawking made a dramatic public concession. At a physics conference in Dublin, he announced that he had been wrong. He now believed that information is preserved, that black holes do not permanently destroy information, and that the information somehow escapes in the Hawking radiation through subtle quantum correlations that are extraordinarily difficult to detect or calculate. The announcement made international news. Hawking had conceded the black hole war, but the concession came with a caveat. While Hawking accepted that information is preserved in principle, the mechanism remains unclear. Nobody has demonstrated exactly how the information gets out. The correlations in Hawking radiation that supposedly encode the information are so subtle that they may be impossible to measure in practice. The information paradox, while widely believed to be resolved in favor of information preservation, is not yet fully solved. It remains one of the great open problems at the intersection of quantum mechanics and gravity. For a kugelblitz specifically, the information paradox takes on an especially vivid character. The information that falls in is the complete quantum state of the electromagnetic radiation. Every photon had a frequency, a polarization, a phase, a direction of travel. All of that information was encoded in the radiation field. When the event horizon forms and the black hole eventually evaporates, all of that information must somehow emerge in the Hawking radiation. But the Hawking radiation appears to carry no trace of it. Where did the information go? The conceptual clarity of a kugelblitz, starting with pure radiation and ending with pure radiation, with a black hole in between, makes the paradox especially clean. You start with organized light. You end with disorganized light. Something happened in between that scrambled everything. And even after Hawking's concession, even after decades of work by the brightest minds in physics, we still don't fully understand what. There is a beautiful symmetry in this. Light goes in, light comes out. The kugelblitz begins as electromagnetic radiation and ends as electromagnetic radiation. In between, there's a black hole, a region of infinitely curved space-time that holds the energy captive for some period, whether a Planck time or trillions of years depending on the mass. But eventually the black hole surrenders. It gives the energy back. Not in the same form, not with the same organization, not carrying the same information in any recoverable way, but the same total amount of energy. The universe's books are balanced. Energy is conserved. And once the black hole is fully evaporated, what remains? Nothing. No remnant, no core, no seed, just empty space-time and a faded cloud of Hawking radiation expanding outward at the speed of light. The region of space where the event horizon existed returns to normal. Space-time uncurves, the geometry flattens. It's as if the black hole were never there, except for the radiation now spreading through space, carrying the energy that once formed it. A kugelblitz is, in the deeper sense, a temporary structure. It is a transient geometric feature of space-time, a brief enclosure of energy that exists for a while, radiates, and vanishes. It is space-time folding in on itself, holding its breath, and then exhaling. The breath is light. It was always light. This impermanence connects to something even larger. In a universe where all black holes eventually evaporate, even the most massive ones, nothing is truly permanent. The supermassive black holes at the centers of galaxies, the ones containing billions of solar masses, will be the last significant structures remaining in the far future of the cosmos. After all the stars have burned out, after all the matter has decayed, after the universe has expanded and cooled to near absolute zero, the black holes will remain. They will be the final repositories of organized energy in an otherwise empty, cold, dark universe. But even they will eventually evaporate. The last supermassive black hole in the universe will finally radiate away its last quantum of Hawking radiation and disappear. And after that, there will be nothing but photons and elementary particles drifting through an ever-expanding void. The universe will end as it began, filled with radiation. A kugelblitz, if one could ever be created, would be a miniature preview of this cosmic endgame. Light becomes a black hole. The black hole becomes light again. The cycle completes, and the universe moves on, indifferent to whether the energy ever paused inside an event horizon or not. We have followed the physics from beginning to end. We started with a single photon, a massless particle carrying a tiny packet of energy. We showed that energy and momentum, not mass alone, are what curve spacetime in Einstein's general relativity. We demonstrated that if enough electromagnetic energy is concentrated into a small enough region, an event horizon forms, trapping the radiation behind its own gravitational barrier. We gave this theoretical object a name, a kugelblitz. We described what an observer would see as it formed, and we explained that the resulting black hole would be identical to any other black hole of the same mass, charge, and spin. We even followed the black hole to its eventual death through Hawking radiation, watching it return all its energy to the universe as thermal radiation. The physics is consistent. The mathematics is sound. General relativity permits it without ambiguity. But permitting something is not the same as making it happen. The laws of physics also permit you to shuffle a deck of cards and deal them out in perfect numerical order, by suit, ace through king, 4 times in a row. The probability is not zero. It is permitted by the laws of nature, but it will never happen in the lifetime of the universe because the odds are so overwhelmingly against it. A kugelblitz exists in a similar conceptual space. The question is not whether the equations allow it. They do. The question is whether the universe will ever actually produce one. And the answer, as far as we could tell from everything we know about physics, engineering, and astrophysics, is almost certainly no. At least not through any means we can currently imagine. And the reasons are not just practical difficulties that some future civilization might overcome with better technology. Some of the obstacles are rooted in the fundamental physics of quantum fields. Nature itself may actively prevent a kugelblitz from forming, even if you had unlimited energy and perfect engineering. Let's start with the most obvious obstacle, the energy requirement. We touched on this earlier, but it is worth revisiting because the numbers are so extreme that they resist intuition. To form a kugelblitz with a Schwarzschild radius of 1 meter, about the size of a beach ball, you would need roughly the mass energy equivalent of the planet Saturn, focused into a sphere 1 meter across, from every direction simultaneously. Now, the total energy output of the Sun is about 3.8 times 10 to the 26 watts. That is already an almost inconceivable rate of energy production. But even if you could capture every last photon the sun emits, collecting them with a hypothetical perfect shell surrounding the star, you would need to collect for roughly 5 billion years before you accumulated enough energy to attempt a 1 meter KOO gel blitz. 5 billion years of the sun's entire luminous output, stored with perfect efficiency, losing nothing. And that is just the energy collection problem. The focusing problem is far worse. You don't just need the energy to exist. You need it to converge all at once, from every angle, onto a target 1 meter across. Every photon must arrive at the same location within the same instant. If some photons arrive early and others arrive late, even by a tiny margin, the energy density never reaches the threshold. The early photons pass through the target region and fly out the other side before the late photons arrive. You need simultaneity across a sphere of incoming radiation, and the precision required is beyond anything the word precision was designed to describe. We're talking about timing accuracy across astronomical distances that would need to be coordinated to within fractions of a billionth of a second. Remember the scale we discussed earlier? The most powerful laser system on Earth delivers roughly 2 megajoules per pulse, an energy whose Schwarzschild radius is smaller than the Planck length. Every laser on the planet fired simultaneously into a single point wouldn't come within countless orders of magnitude of the threshold. The gap between what humanity can produce and what a KOO kugelblitz requires is not an engineering gap that better technology could close. It is something closer to a civilizational impossibility, a difference so extreme that the comparison itself becomes meaningless. But suppose, for the sake of argument, that some unimaginably advanced civilization solved both problems. Suppose they had access to energy sources that dwarf our sun by factors of billions. Suppose they developed focusing technology of supernatural precision, able to direct radiation from every direction onto a subatomic target with perfect timing. Would they succeed? Would a KOO gel blitz form? Probably not, because there is a third obstacle, and this one is not about engineering at all. It is about the fundamental behavior of electromagnetic fields at extreme intensities. And it may represent a genuine physical barrier, not just a practical one, that prevents a KOO gel blitz from ever forming regardless of how much energy or technology you throw at the problem. The obstacle is called the Schwinger effect, named after the American physicist Julian Schwinger, who first described it in 1951. The Schwinger effect is a prediction of quantum electrodynamics, the quantum theory of electromagnetic fields, and their interactions with charged particles. It describes what happens when the electric field strength in a region of space becomes extraordinarily intense, and the result is devastating for any attempt to create a KOO gel blitz. To understand why, remember what electromagnetic radiation actually is. It is an oscillating electric and magnetic field propagating through space. A photon is a quantum of this field. When many photons are packed closely together, when the energy density of the electromagnetic field becomes very high, the electric field strength in that region becomes enormous. Under normal circumstances, this is not a problem. Strong electric fields exist in many contexts, inside atoms, near the surfaces of charged objects, in laboratory equipment. But at a certain threshold, when the electric field reaches a critical value known as the Schwinger limit, something extraordinary happens. The electromagnetic field becomes so intense that it begins to spontaneously produce matter. Specifically, it creates pairs of electrons and positrons directly from the energy of the field itself. This is not science fiction. It is a well-established prediction of quantum electrodynamics, one of the most precisely tested theories in all of science. QED predictions have been verified to more than 10 decimal places of accuracy. The Schwinger effect has been partially observed in laboratory settings, and the theoretical framework behind it is not seriously in doubt. The critical field strength at which electron-positron pairs begin to appear spontaneously is approximately 1.3 times 10 to the 18th volts per meter. This is an incredibly strong field, far beyond anything we can produce with current technology. But it is not beyond the field strengths that would exist inside a converging radiation shell as it approaches kugelblitz energy densities. Here is why this is a problem. Long before the energy density of the converging radiation reaches the threshold needed to form an event horizon, the electric field strength crosses the Schwinger limit, and when it does, the electromagnetic energy begins to convert into electron-positron pairs. The pure radiation field bleeds energy into the creation of massive particles. Each pair that forms carries away energy from the radiation field. This energy is no longer available to contribute to spacetime curvature. The very process you are trying to achieve, concentrating electromagnetic energy to the point where spacetime curves shut, is undermined by the quantum nature of the electromagnetic field itself. The field destroys itself before it reaches the critical density. Think of it this way. You're trying to fill a bathtub by pouring water in faster and faster, but the bathtub has a drain at the bottom, and the drain gets wider the more water you pour in. The faster you add water, the faster it escapes through the drain. You can never fill the tub because the drain keeps pace with the faucet. The Schwinger effect is that drain. The more electromagnetic energy you concentrate, the more of that energy is converted into matter, electron-positron pairs that carry the energy away in a different form. The radiation field is being siphoned off, converted into particles with rest mass, before it can achieve the density needed for gravitational collapse. Now, you might think the created electrons and positrons themselves have energy, and that energy should still contribute to space-time curvature. And you would be right. Electron-positron pairs do carry energy and momentum, and they do curve space-time. But there is a crucial difference. Electrons and positrons have rest mass, and they behave very differently from photons. They interact electromagnetically, scattering off each other and off the remaining photons. They annihilate when an electron meets a positron, producing new photons that radiate outward. The system becomes chaotic. Instead of a clean, organized shell of radiation converging inward, you get a turbulent, disorganized mess of photons and particle-antiparticle pairs. Some moving inward, some moving outward, energy being constantly converted back and forth between radiation and matter. The organized convergence you need to maintain for gravitational collapse is disrupted. And this is not a minor disruption. The Schwinger effect does not merely shave off a small percentage of the energy. At the field strengths needed for a KOO gel blitz, pair production would be explosive. The electromagnetic field would cascade into particles, creating a blizzard of electrons and positrons that interact with each other and with the remaining radiation, feeding back into the system in ways that are extraordinarily difficult to model precisely. The net result is that the energy you invested in creating a coherent, converging radiation field gets scattered and randomized. Some of it flies outward as newly created particles. Some of it is re-radiated as photons moving in random directions. The clean geometry of inward converging light is shattered. Some physicists have examined whether you could somehow outrun the Schwinger effect by pouring energy in faster than the field can convert it to particles. The idea would be to increase the energy density so rapidly that the event horizon forms before pair production has time to drain enough energy away. But this approach faces its own problems. The Schwinger effect is not a slow, gradual process at very high field strengths. The rate of pair production increases exponentially as the field strength rises above the critical threshold. The higher you push the field, the faster it bleeds energy into particles. It is not clear that any rate of energy input could outpace this exponential drain. The mathematics suggests a race that the radiation field cannot win. There is also a more subtle obstacle, one that has nothing to do with quantum mechanics and everything to do with gravity itself. Even if you could somehow suppress pair production entirely through some unknown mechanism, the gravitational dynamics of converging radiation at extreme energies create their own problems. As radiation converges inward and the energy density climbs, space-time begins to curve. And that curvature, the very effect you are trying to produce, starts to interfere with the precise geometry of the convergence. Think about what the converging radiation is doing. It is arriving from every direction simultaneously, aimed at a single tiny point. This requires perfect spherical symmetry. Every photon must arrive at the same location at the same instant. But as the energy density grows and space-time curves more steeply, the curvature acts as a gravitational lens. And gravitational lenses are not perfect optical instruments. They focus light, yes, but they also distort it. A perfectly symmetric, evenly distributed shell of inward-moving radiation would produce a perfectly symmetric gravitational field, which would in turn focus the radiation evenly. But perfect symmetry doesn't exist in the real world. Any tiny imbalance, any slight excess of energy arriving from one direction compared to another, gets amplified by the curvature. Here is why. Suppose slightly more energy arrives from the left than from the right. The space-time curvature on the left side becomes slightly steeper. This steeper curvature focuses the left side radiation more tightly, increasing the energy density on that side even further. The asymmetry grows. Meanwhile, the right side, with slightly less energy, curves less steeply, focusing less effectively, falling further behind. A small initial asymmetry becomes a larger asymmetry, which becomes an even larger one. The feedback loop amplifies imperfections rather than smoothing them out. The perfectly uniform, simultaneous convergence required for a kugelblitz becomes harder and harder to maintain as the curvature deepens, because the curvature the radiation has already produced distorts the paths of the radiation still arriving. The result is that instead of a clean, spherically symmetric collapse, you might get an irregular, lumpy concentration of energy. Some regions reach high density while others lag behind. Energy that was supposed to converge uniformly instead piles up in some areas and thins out in others. The precise conditions needed for a simultaneous event horizon formation across the entire sphere are disrupted by the very gravitational effects the convergence is trying to create. The radiation is fighting against its own gravity, not because gravity repels it, but because gravity distorts the careful geometry that makes the collapse possible. Modeling this feedback loop in full detail requires solving Einstein's field equations in a highly dynamic, non-linear regime, which is among the most challenging problems in theoretical physics. No complete solution exists for this scenario. Given all these obstacles, what about natural processes? Could nature create a kugelblitz even if human technology cannot? Are there astrophysical environments where enough electromagnetic radiation is concentrated intensely enough to form a radiation-based black hole? The short answer is that no known natural process produces anything close to the conditions required. The most natural place to look is the most energetic events the cosmos produces: gamma-ray bursts. These are the most violent explosions in the universe since the Big Bang itself. A single gamma-ray burst can release more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. Some of the most energetic gamma-ray bursts release roughly 10 to the 47th joules, comparable to the rest mass energy of the sun, all concentrated into a few seconds. Surely that must be enough. It is not, and the reasons reveal exactly why a kugelblitz is so difficult. A gamma-ray burst does release an extraordinary amount of energy, but that energy is not converging inward. It is expanding outward, violently outward. Gamma-ray bursts produce narrow relativistic jets, beams of radiation and matter shooting away from the central engine at speeds approaching the speed of light. The energy is collimated, focused into a cone typically a few degrees wide. But within that cone, it is expanding, not compressing. The radiation spreads across volumes measured in light seconds or even light minutes as the jet propagates. The energy density within the jet, while extreme by any human standard, is diluted over an enormous volume. It is like comparing a fire hose to a hypodermic needle. A fire hose delivers tremendous total energy, but spread across a wide area. A kugelblitz would require all that energy concentrated into a subatomic point. The geometry is entirely wrong. Even at the source of a gamma-ray burst, in the immediate vicinity of the collapsing star or merging neutron stars that power it, the energy density of the radiation alone is far below the threshold for a radiation-only event horizon. The event horizons that do form in these environments, and they do form, are produced primarily by the gravitational collapse of matter, not by the concentration of radiation. The photons contribute to the total energy budget, but they are a secondary player. The matter dominates. No known astrophysical event produces the conditions needed for a pure radiation black hole. Inside stars, the energy density of photons is high. The core of our sun contains a tremendous amount of electromagnetic radiation, photons bouncing from atom to atom in the dense plasma, taking tens of thousands of years to diffuse from core to surface. But this radiation is in thermal equilibrium with the matter surrounding it. The energy density of the radiation, while high, is still far below the level that would produce significant space-time curvature, independent of the matter that dominates the star's gravitational field. The photons inside a star are gravitationally significant, contributing to the star's total energy and therefore to its space-time curvature. But they are not concentrated independently of matter. There is no natural mechanism that separates radiation from matter and focuses it into a kugelblitz. In the very early universe, during the radiation-dominated era we discussed earlier, the energy density of photons was extraordinarily high. The universe was filled with a hot, dense photon gas, but this radiation was uniformly distributed across all of space. There were no localized concentrations intense enough to form individual event horizons. The radiation drove the expansion of space-time as a whole, curving the geometry of the entire universe. But it did not collapse into isolated black holes because it was spread too evenly. Black hole formation from radiation would require a significant departure from uniformity, a region where the energy density was dramatically higher than its surroundings, and the early universe was remarkably smooth. The tiny fluctuations that did exist were only about 1 part in 100,000. far too small to trigger gravitational collapse of the radiation field into individual event horizons. Some physicists have speculated about primordial black holes that might have formed in the very first instance after the Big Bang when conditions were extreme and exotic. It is conceivable that in certain models of the early universe, localized energy density fluctuations could have produced tiny black holes. But even in these speculative scenarios, the formation mechanism is usually attributed to density fluctuations in the overall energy content, which at that time included both radiation and matter in various forms. These hypothetical objects are not kugelblitzen in the pure sense. They are density fluctuation black holes, and their existence remains unconfirmed by any observation. So where does all this leave us? We have followed the chain of reasoning from start to finish. Photons have no rest mass, but they carry energy and momentum. Energy and momentum curve spacetime. Enough energy, concentrated in a small enough volume, curves spacetime past the point of no return, forming an event horizon. The equations of general relativity describe this process clearly, without ambiguity, regardless of whether the energy comes from matter or from radiation. A black hole formed purely from electromagnetic radiation is called a kugelblitz, and the physics permits it. But the universe appears to prevent it, or at the very least, makes it extraordinarily difficult. The energy requirements are so far beyond anything humanity can produce that they belong to a different category of impossibility than ordinary engineering challenges. The focusing precision needed is beyond anything we can imagine, let alone build. The Schwinger effect, the spontaneous creation of electron-positron pairs from intense electromagnetic fields, actively drains energy from the radiation field before it can achieve the density needed for gravitational collapse. And the gravitational feedback between converging radiation and curving spacetime amplifies any imperfection in the symmetry of the convergence, making the precise geometry needed for a clean collapse almost impossible to maintain. Quantum electrodynamics intervenes from one direction. General relativity's own nonlinearity intervenes from another. The kugelblitz is caught between two barriers, each one formidable on its own, and together perhaps insurmountable. No kugelblitz has ever been observed. No natural process is known that could create one. No laboratory experiment comes within countless orders of magnitude of the required energy density. The kugelblitz exists as a mathematical solution to the equations of general relativity, a thought experiment that reveals deep truths about the relationship between energy, mass, and gravity, but not as a physical object that has ever existed in the observable universe, as far as we know. And yet, the concept matters. It matters because it teaches us something fundamental about the nature of gravity. Gravity is not about mass, it is about energy. Any form of energy in any configuration contributes to the curvature of space-time. This insight, which seems abstract when stated in words, has real and measurable consequences. It explains why the radiation-dominated early universe expanded the way it did. It explains why light bends around massive objects. It explains why the photons trapped inside the sun contribute, however slightly, to the sun's gravitational field. The kugelblitz is simply the most extreme expression of this principle, the logical endpoint of asking what happens when you take the gravitational effect of light and push it as far as it can possibly go. The concept also matters because it illuminates the boundary between general relativity and quantum mechanics, the two greatest theories in physics that have never been fully reconciled. General relativity says the kugelblitz can form. Quantum electrodynamics says the electromagnetic field will produce particles before the critical density is reached. These two statements are in tension. They point to a regime of physics, the regime of extreme energy density in tiny volumes, where our two best theories give different answers or at least complicate each other's predictions. This is exactly the regime where we expect a theory of quantum gravity. A unified framework that combines general relativity and quantum mechanics would be needed to give a complete answer. And we don't have that theory yet. It remains one of the greatest unsolved problems in physics. So the question of whether a kugelblitz can truly form might not have a definitive answer until we understand quantum gravity. General relativity alone says yes. Quantum electrodynamics raises serious objections. A full theory of quantum gravity might settle the debate, either by confirming that nature has a built-in barrier that prevents radiation from collapsing into a black hole, or by revealing some mechanism we haven't yet imagined that makes it possible under extreme conditions. And that brings us back to where we started, to the question posed by the title of tonight's exploration. What happens when light collapses into a black hole? The answer is both simpler and stranger than you might have expected. Light, despite having no rest mass, carries energy and momentum. Energy and momentum are what curves space-time. If enough light is concentrated into a small enough region, the space-time curvature becomes so extreme that an event horizon forms, trapping the radiation behind the gravitational barrier its own energy created. The resulting object is a black hole, indistinguishable from any other black hole of the same mass, charge, and spin. There is no observation that could reveal it was born from light rather than from matter. The black hole eventually evaporates through Hawking radiation, returning all its energy to the universe as thermal radiation. Light goes in. A black hole exists for a while. Light comes out. The cycle completes. But this process, while permitted by the equations of general relativity, faces barriers so formidable that it may never occur in the real universe. The energy requirements are beyond astronomical. The focusing precision is beyond imagination. And the quantum nature of electromagnetic fields actively works against the process, converting radiation into massive particles before the critical density can be reached. A kugelblitz is a window into the deep structure of reality. It shows us that the boundary between light and gravity, between energy and geometry, between what we think of as immaterial and what we think of as the most powerful force in the cosmos, is not a boundary at all. It is a continuum. Light is not separate from gravity. Light participates in gravity. Light creates gravity. And pushed to its ultimate extreme, light can become the very thing from which it can never escape. That is the paradox we began with. Light is the fastest thing in the universe. The only thing that can trap it is a black hole. And yet, enough light, concentrated in one place, can create the black hole that traps it. The prisoner builds its own cell. The runner creates the wall it cannot outrun. The universe allows this, at least on paper. Whether it will ever happen in practice remains an open question, one that sits at the frontier of human understanding, waiting for a theory of quantum gravity to resolve. For now, the kugelblitz remains a thought experiment. A beautiful, haunting, mathematically precise thought experiment that reveals something profound about the universe we live in. Gravity does not care what you are made of. It only cares how much energy you carry. And if you carry enough, even if you're nothing but light, Even if you have never possessed a single gram of rest mass in your entire existence, you can curve the fabric of space-time so completely that you become a black hole. Not despite being massless, because of the energy you carry. Because in Einstein's universe, energy is all that gravity has ever needed. The next time you see a beam of sunlight streaming through a window, warming your skin, lighting up dust motes drifting through the air, remember this: that light has gravity. Every photon in that beam is curving space-time, pulling on the Earth, pulling on you, pulling on everything around it. The effect is so small that no instrument could ever measure it, but it is real. It is there. And if you could gather enough of that gentle, warm, familiar light, enough of those soft golden photons, and focus them into a space smaller than an atom, they would swallow themselves. The light would create a darkness from which no light could ever escape. That is what happens when light collapses into a black hole. It becomes the thing it cannot outrun, and the universe, vast and ancient and indifferent, allows it.